So today we're starting the final learning objective 4. We're coming down to the home stretch. I just want to say one thing real quick is I've said parts of this throughout the semester, but just to reiterate, if you've made it through LO2, like if you're completing this stuff, you did the makeup quiz and interview, you got that, you got point of sale done and everything. In my opinion, I have to qualify this or else somebody at the end of the semester will be like, you said. So in my opinion, if you can make it through learning objective 2, you're going to make it through the whole course. You're going to be able to stick it out and be able to finish everything. You're doing fantastic if you make it through that. Learning objective 3, I think, is roughly on par in terms of difficulty with LO1. They are very different topics. One we're banning control flow, and one we're banning variables. Very different things, so it depends on what gels with you a bit better. But I think all considered, they're about roughly equal in difficulty. So if you can get through LO2, you can make it through LO3. And then LO4, I think, is a step down in difficulty. I always like to do this in my classes where towards the end of the semester, I'm backing off a little bit. I hit you hard in the middle 2 sections. This is where I'm hitting you hard. This is where you're learning a whole lot of content. All of OOP and FP with a sprinkling of concurrency in there. That's a lot to do, especially in 6 weeks. So I hit you hard there. But at this point, when we go into learning objective 4, we're kind of backing off a bit. So learning objective 4, we're talking about 3 things, and they're all really related: linked lists, trees, and graphs. So 3 different data structures and algorithms that apply to them. And all 3 of the components, read, explain, write, they're just going to hit you with linked lists, trees, and graphs. So what are we going to talk about? What are we going to test you on? What are we going to ask about in the interview, etc.? Linked lists, trees, and graphs. Each one of them has a week, so even the structure of this learning objective I don't know, I think it's just easier to digest in a lot of different ways. Plus, after making it through these 2, learning objective 2 and 3, the content itself, I think, is a lot easier to understand in LO4 as well. In my opinion, this is the second easiest learning objective, next to 1. But also at the time when we're going through learning objective 1, you're learning Scala, you're learning all the syntax of Scala, you're writing tests for the first time, figuring out what the hell a unit test is, what are Jesse's incorrect solutions, what the hell does that even mean? You're going through a lot of brand new stuff during learning objective 1. So when we get to learning objective 4, I think it'll feel like the easiest learning objective. And I like backing off at the end of the class, at the end of the semester, because I know that's when like every other course in existence likes to hit you the hardest. So if I'm taking your time in the middle of the semester and then backing off towards the end, I think that helps you with your overall time management, your overall planning of the semester. So learning objective 4, let's start it. We're going to start talking about linked lists. I posted the link for homework 4, at least I thought I did, on Friday. I was all happy because I was getting ahead of it by a few days. I usually aim for the Monday when the content starts. But apparently my website didn't update. So I pasted the link in the lecture channel on Discord so you can see the last project. And as soon as I get home and settle in and figure out what the hell happened with my website, I'll update the website and get the link on here for you. The link, I hope it's still on my clipboard. Should be, yeah. So for this one, I give you the structure of a game. There is a lot of starter code here, but all of the code that you write is in one single class. So you go in a file and write that. You can create more classes and helper methods and all that stuff, but all of your code is in one file. So don't get too scared that there's a lot of starter code. There's one particular file in there where all 6 lecture tasks and both application objectives, all of that will go in the same file. So you're not navigating the entire code base the whole time. You do have, especially now that we covered concurrency, you have what you need to understand all of the code, all of the starter code. So if you do want to look through it, there shouldn't be anything in there that'll really catch you off guard. It might take some more practice to be able to read concurrent code. I use both actors and WebSockets to be able to get this game working. So it might take a little bit just because that content was just presented last week, and that content comes and goes pretty fast. But you can understand all that. So what we'll build is a game. You'll be able to see the structure of the game, but nothing interesting will happen when you first boot it up until you start completing the lecture tasks. and especially the objectives at the end. All these red squares are going to be enemy spawners. They're going to spawn enemy AI. Of course, they won't do anything until you complete the homework, until you start working through the homework. But those will spawn enemy AI, and as you complete the homework, they'll start hunting you down and shooting at you, and they'll also attack each other. They won't discriminate against human and AI players. They're going to attack the closest player they find and start firing once per second at that player. Then you can move around and fight the enemies as you walk around this map. The only other thing I want to point out, we'll talk about the lecture tasks as they come in lectures, but I am going to ease up on the lecture tasks themselves. Complete any 5 of the 6 lecture tasks for this one. So if there's that one test case that you're banging your head against and you just can't figure out, skip it for this one. Just go move on to another lecture task, finish that one, get your 5, and get out of there. Get out of this assignment and go focus on your other finals and your projects and everything else. And the interview and quiz for this one, of course, too. Oops. I forgot my keyboard shortcut. What's up, Dragos? Is AOs for genetic algorithm harder than AOs for enemy AI? I get this question so much. Not this exact question, but what are the easiest AOs to be able to get my A is basically what the questions all boil down to. Let me give my rundown. The ones in homework 1 were, of course, the easiest, but those opportunities have gone. For point of sale, I think those are both pretty difficult. For point of sale, if you got those or not, the difficulty with those is in your understanding of the state pattern. So if you really knocked LT6 out of the park and you have a really good grasp on the state pattern, then I don't think the AOs are too hard. But what happens usually with homework 2, with point of sale, is that students just barely stumble through LT6. And since I ease up on the requirements, so you can be failing a few of my tests and you can get a few of my incorrect solutions, not correct or not marked as wrong. Since I ease up on that, what students tend to do is not actually complete LT6, but jump into AO1, and you just can't do that. If you don't have LT6 completely done and really done well, you can't really go into the AO. So for some students, they feel really hard if you fall into that trap. You really got to finish LT6 and really crush it before you go into the AO. So a lot of students think those are a lot harder. For genetic algorithm, AO1 is pretty tough. You have to have a really good grasp on recursion and these first order functions, passing functions around your code and things. But it's not a huge leap up from the LTs. It definitely is a leap up. And then AO2 on genetic algorithm, unless you're really solid on the content, I feel weird even saying this, but unless you're really solid on the content, don't even waste your time on it. It's tough. Like, that's definitely the hardest application objective of the semester is AO2 of genetic algorithm. It's in just the one-line summary of it. You're training, you're using a genetic algorithm to train a neural network to be able to identify irises. Like, that's ridiculous. That's a lot. And it's made to be that. It's made to be more so than any other application objectives or any other portion of this course. It's made to be the extra challenge for somebody who is just really getting all of the content, really excited about computer science, and especially if you're interested in going into AI. Like, that's your application objective. And since there are more application objectives available than you need for an A, I can use at least one of them to be able to be that extra challenge. The intent is actually for every AO2 to be like that, but I do ease up on a lot of the AO2s. I don't make them too ridiculous. I don't make them too hard. So that one's by far and away the most difficult one of the semester. There's a lot going on there. Even just to read through all of my stuff, I feel like there's a page and a half of content just for that AO, explaining everything. So that one's really tough. The genetic algorithm in AO1, not too bad. I do recommend doing that one, though, because that's where the whole assignment comes together. That's where you actually build the genetic algorithm. I couldn't get you to build the genetic algorithm. Like I didn't have a good way of breaking that down into lecture tasks, so I really couldn't get you to build it in the LTs. I had to push it off to the AO. So I recommend doing that just to see the assignment. The intent, I got to finish my thought there. The intent is for you to be able to get every AO1. Like if you're going for an A, the typical path in my mind, get every AO1 on the homeworks and then the 2 from the final exam. You don't need to get any of the AO2s. That's how the course is designed. And then if you get AO2s, that's where you start working towards skipping the final. For homework 4, I don't think the AOs are too difficult. I don't think they're as hard as the ones on genetic algorithm. You may or may not disagree depending on your grasp of the content. I think AO1, especially on the final homework, is pretty easy if you're able to get lecture tasks 5 and 6. It's very similar to lecture tasks 5 and 6. It's just like the next logical step. And I show you how to do it in the lecture slides. You just have to convert that to code. So AO1 on the last homework, I think, is fairly free. AO2 on the last homework, it's a little bit of a jump up from that. It's definitely not free. And it's a little tough to understand what's going on. There's a lot of moving pieces, and you really have to understand some of the handout code, some of the structure of the project to be able to get that. But once you do, I don't think it's too hard to get. It's definitely not as hard. I'd say it's not even as hard as AO1 on homework 3. For AO2 on homework 4. Homework 4, the AO's not too tough, not too bad. So that's your chance to get a couple more AOs before going into the final. And I think, if I remember right, I think there's a way to cheese AO2 on homework 4, just a little bit. It's definitely not as difficult as I intended. I think there's a way students have cheesed it last semester, where they just didn't have to understand. It's about trees, and they didn't have to understand trees as much as I wanted to require them to. So not as hard. So that's my rundown. I get that question a lot, so hopefully that answers that. If somebody asks again, I can just send them the timestamp to this lecture, so I don't have to go through it every time somebody asks. But that's my rundown. Anybody else have questions like that, by the way? I have not been in a slides mood today, so I would rather just talk to y'all. Anybody else have questions? I mean, I'll still cover the slides, of course, but. I see it. I look at someone's typing in the chat. Oh, but it's Rin. It's a TA. Oh, because there's a question on this. How's the final compared to the final exam? Oh, yeah. That's the next thing I should mention. So the final exam AOs, they're very different than any of the programming AOs. So the final exam, the structure is, here's a description of a program. Like, here's what the user wants, the end user. How would you design the software? I don't want actually any code for that, but how would you design it? And specifically, I'm going to ask 4 questions, 1 for each AO. And the question is going to be, where would you apply the concepts from this application, or the LO, learning objective? Where would you apply the concepts from this learning objective in your software? So for LO1, how are you going to test this? What specifically are you going to make sure you test? So for example, if I say, make a banking app, and it needs to support withdrawals, deposits, transfers between accounts, you all have some list of features. What are you going to test for that, and how are you going to test it? How are you going to write those unit tests? So give me like a few sample test cases, specific methods that you designed that need to be tested, etc. If you have objects, like making sure that you're testing the state of the objects, things like that. Things we've been doing all semester in your test suites. What specific challenges would come up in your design? For OOP, where are you going to use objects? Where are you going to use classes? Where are you going to use inheritance? Where are you going to use polymorphism? So maybe it's a banking app where there are different types of bank accounts. You have an abstract class bank account, and then checking account extends that, savings account extends that, credit card extends that, etc. So like explain to me where are you going to use OOP in this design? Where are you going to use FP and or concurrency in your design? And show me one place where you can use a linked list, a tree, or a graph. Actually, for that one, I exclude linked list because that one's too easy, but where are you going to use either a tree or a graph? And then that one's usually a little bit contrived, but come up with some place where you can be like, here's where I could use a tree. I would use this. I would have a tree of transactions. I don't know. Come up with something. And just show me that you can apply the whole idea of the application objectives. Show me that you can apply the concepts from the learning objectives to real-world software. So the final exam does that in a much more direct way than the other application objectives of the course. It's just here's a real-world problem. Apply what you've learned in this class to design your software to solve it. And as long as you do all that stuff, it's really to be honest, as long as you understand the content of the course at a pretty good level, it's hard to not get those AOs on the final. I try not to drill you too much. It's just show me that you've learned stuff in this course. If you made it all the way to the final exam, you've probably learned a frick ton of stuff. So just show me what you've learned all semester. Reflect on all the content and show it to me in that final exam. If you made it through all the assignments, all the interviews, and all the quizzes, like all that information's in your head, just put it to paper for the final. What grade do you need to apply to become a TA? There are no grade requirements. At the end of each spring semester, we send out an email to all CSE undergrads, inviting you to apply. So next semester, at the end of next semester, look out for an email. If you don't see one, email me directly and be like, hey, you said there'd be an email, and I'll send you the application process, just in case you missed it. It goes to like the CSE undergrad listserv, so look out for that at the end of the spring. There's no GPA requirements. There's no grade in the course requirements. Some of my best TAs are students who got C's in my classes. There's no requirement. What we're really looking for with TAs is, can you take the content of the course and explain it well? If you can do that, that's the biggest qualification to be a TA. And sometimes students who did poorly in my classes do make the best TAs, as long as they do understand the material by the time they're applying. Like by the time they get to the end of 250, 220, they know the 116 material by then, so I'm not too concerned about that. And then in office hours, those TAs really do tend to do well because they understand the struggle you're going through. Like a student comes to office hours and just doesn't understand the material. That student who got a C in 116 knows what you're going through. The student who just breezed through with an A might not be able to understand your questions even. I've seen that problem in the past, so I don't even look at your grade in the course, to be honest, when I review applicants. I look for teaching experience. If you have teaching experience, that's always a plus. I look for, did you clearly just throw your resume together in a few minutes before you applied, or did you take some thought and care into it? That's a big thing for a lot of applications. I don't want to go too far down this thing, but like take pride in your work. If you don't take pride in your resume, something that you have like absurd amounts of time to work on and something that means so much for your application, it's one of the only things we actually get to see. If you don't take pride in that, you're not going to take pride in any of the work you do as a TA or any job you apply to. So that's an easy thing to be able to put people in the reject pile. If you didn't put any effort into your resume, I know you're not going to try hard at the job. So that's an easy reject. But if you have a nice looking resume that you clearly cared about and put thought into, and if you have any teaching experience at all, you're at least going to make it to an interview. And then if the interview, we asked you to do a teaching presentation. So just to pick a topic from 115 or 116 and present it to us in 10 minutes. If you can explain all the topics well, then it looks really good for you. So anyone who's interested in becoming a TA, that's the process. Yeah, there's no, you got a B in 116. We're not going to take it. There's none of that. Weird Alex, who is it? I need names. It's hard for me to hear what's going on out there. If somebody's being belligerent like that, Many names. Who is it? But anyway, anyone who has their sound on their laptop, like, cut it out. Like, cut the shit. Why? Why are you doing that? All right. But yeah, all these rooms, the sound's designed to go that way, so I can't even really hear when people are being annoying like that. So if they are, I mean, first of all, when I can hear you, sometimes some of you I can hear, that means you're being extremely loud. And then that's when I start pausing lecture for a second and just stare at you. If I'm staring at you during lecture for a long period of time, it means you're being loud. But anyway, let's get into some content, or else this whole lecture will slip away from me. Yeah, it's probably Dragos. Damn it, Dragos. All right, linked lists. So let's quickly review arrays before we talk about linked lists, because the comparison is the more interesting part for between arrays and linked lists. So arrays, this is one continuous block of memory. We said this way back in the semester. It seems like forever ago. But it's one continuous block of memory. And to be able to get a specific element at an index from an array, we're going to do just a little bit of math. We're going to take the memory address of the first index, and we're going to add to that the index that we want to get times the size of each element. So arrays have to be fixed size elements. Like if we have an array of doubles, 64 bits for each value. So we take 64 bits, or 8 bytes, times the index we want to get, add that to the memory address of the first byte, and that's the memory address where we're looking, where we're going to find our data. So we take the index, do a little math, and we find exactly where that element is, and we can go to that memory address and access that element. So these are fixed size. If we want to expand the size of an array, we actually have to create a brand new array, copy all the values over, and then delete the old array. So it's really expensive to expand the size of an array. And in memory, it looks like this. We're going to have this array in the heap, and we're going to have a reference to the memory address of the first value in that array. And then from this memory address, we're going to do that little bit of math. If we want to get the value at index 2, we're going to take 2 times the size of an element and go right to this memory address and be able to get that memory. If this is an array of size 1 billion, it's still just as fast. A little bit of math and then go to that memory address to be able to get the value that we're looking for. And this is what we call random access. We can just access any element as long as we know the index of the element we're looking for. We can just go directly to that element. That's why we call it random access memory, RAM, because RAM is effectively one giant array. Whenever we're talking about like memory addresses, when we visualize the stack or the heap, we always have those memory addresses. Those memory addresses are our RAM. It's all one big random access array of gigabytes of values, but it's all just arrays. It's an array of bytes. That's what your RAM is. And you can randomly access any byte that's stored in RAM. Linked lists, on the other hand, they're still sequential data structures, so there's still a defined ordering, unlike maps, any key value store, dictionaries, objects in JavaScript, Python and JavaScript respectively. But linked lists are spread across memory. Every value is at some place in memory. We don't know where, we don't care where, but every element knows the memory address of the next value in the list. So each value can be anywhere, but each value knows the memory address of the next value of the list. So in this way, we can still traverse the list by hopping all around memory. Now, this doesn't give us the random access that we had with arrays, so it's going to take a while to get to if we want to get to the 100th element of a list, we have to go hop around 100 times around memory, so it's very inefficient that way, but it gives us the advantage that it has variable size. To add an element to a linked list, it's no big deal at all. We just add another element and then have that update the references to be able to add that element to the list. We just get memory anywhere in the heap, and then through references, we're going to refer to that in the list. So in memory, it's going to look like this. In the stack, we're going to have a reference to the first value in the list, just like we did with arrays, except now what's stored at that value is going to be the actual value in the list and a reference to the next element in the list. That's going to have the element that it has and a reference to the next element, which is going to have its value. And then when we get to the last one, we're going to set its next to null to be able to signify this is the last element of the list. There's nothing more to read. And when we see this, we call this null terminated. We say this is null terminated. There are a lot of different ways to set up a linked list. I like to do it as null terminated because you're going to see that a lot in 220. Even your strings are going to be null terminated. So I want to get you used to seeing that keyword null, which we normally wouldn't see in Scala. The Scala community doesn't really like the keyword null, doesn't like to use that at all. We're going to use it because you're going to see it when you start working with C in 220. So you have a little bit of a practice with that one. What are some of the main differences between a list and a linked list? Lists are usually linked lists. Like Scala's list, the list we've been using all semester, it's a linked list. They just call it list instead of linked list. That's not true in every language, but in Scala, that is true. Like in Java, what's an array list? Is it an array or a list? I don't know. It's actually an array is the actual answer. I do know, but by its name, you wouldn't know if it's a linked list or an array. All right, so this is what it'll look like in code. And this is I won't say the entirety, I guess. This is the entirety of the structure of a linked list. We're going to have a class called linked list node, which is going to know the value of the linked list that it refers to, and a reference to the next linked list node. And that's it. That's our linked list. We're going to add to this class. If you look at it in the repo, there are more methods inside this that help us work with a linked list of this structure. But this is it. This is the whole structure of a linked list. So when you interview somebody, your TA asks, "What's the structure of a linked list?" Well, it's made of a bunch of nodes where each node knows the value of the linked list that it stores, and a reference to the next linked list node. Like that's it. I guess that's not it. The last linked list node will have a reference to null, and on the stack, or any variable that stores a list is only a reference to the first node in that list to fully complete that. But that's the structure of a node. We're going to bring back our old friend type parameters so we can have a linked list of any values. Just like any list we've created all semester, it has to be a list of ints or a list of strings or a list of doubles or a list of characters. So same thing here. We're going to have our linked list node take a type and then create linked lists of that type. So here I'm creating a linked list of ints, and I'm going to build this individually one node at a time. I'm going to create a new linked list node of ints with the value 1 and next of null. Then I'm going to create a new linked list node with the value 3 that takes a reference to the old linked list, the linked list node that I just created. So its next is going to be that list. I'm going to create and overwrite my variable, which such a relief getting into LO4 and starting to use variables again. I miss variables throughout LO3. And then create another linked list node that stores 5 with a reference. Its next is going to be this list, which is the one with 3, which is next is 1, which next is null. And that's what I'm going to store in my list. That's going to be the actual list. This is going to be a mutable list. Scala's list that we've been using all semester is immutable, as we saw a few weeks ago. But we are going to build a mutable list. These are going to be variables for our class. You will see immutable lists. I believe they're still covering immutable lists in 250. There was an instructor change there, so I'm not sure if any content is going to change. But if not, you'll cover immutable lists in 250, which is a pretty interesting topic. First, we're going to create a linked list node with value 1 and next of null. So on the heap, I'm going to get my linked list node object with those values, and I'm going to store that in a variable named myList on the stack. So on the stack, I have a reference to that object that I created, which is all stuff we've seen before. Where it gets a little tricky, just the way I wrote this code, I guess, is the next line. When we create this line, at this point, myList stores the reference at 416. So when I create this new linked list node, myList is at 416, and then the value is 3. So I ask for a new object, give me a new object on the heap of type linked list node. It's going to be at some random spot. I'm going to say 795. I'm just making up these numbers for the slides, as always. The value 3. And then since my list was 416, when this constructor was called, that next value is going to be at 416, the reference to the other linked list node that I've created. At 795 is what's returned, and then I reassign that to the myList variable. So myList is now a reference to that new node that we just created, and that new node we just created has a next as a reference to the first node that we created. Same thing with the next value. myList is now at 795. So when I create this new node, myList is at 795. That's what gets put in the next variable of this linked list node. And when that's created, it's going to return, again, some random number. I chose 506. I don't know why. Those are the numbers my fingers hit when I made this slide. And returns 506. I'm reassigning that to myList. So myList, by the end of these 3 lines, is going to store a reference to this at 506, which has the value 5 next of 795, value 3 next of 416, or the value 1 next of null, so we know we've reached the end of the list. Now it's important to get the order of these. You'll see something like this on your quiz. I can just about guarantee that. And what students like to do is just glance at the code fairly quickly. I mean, you're under pressure and stuff, I understand. But you glance at the code, you see 1, 3, 5. And when the question asks, what are the elements of this list in order, you put 1, 3, 5. Make sure you're going through this, and especially when you trace through the program, make sure you're focusing on what's going on the stack and heap, so you understand that this myList at the end is going to be the list 531, not 135. So if you break it down and you break this line by line and trace through the stack and heap and every little motion that's going on in this program, you're never going to make that mistake. But if you just glance at this and don't think about it too much, you might end up putting 135 on that, and then when we're grading the quiz, we're like, well, you clearly didn't follow what's going on, so we know you got that one wrong. So just a heads up on that. When you see code like this with linked lists, make sure you're getting the order of that list correct. It's just a mistake I see so often. I don't like taking, marking you off or something like that. I mean, I have to, and the TAs have to, but it's just a frustrating thing to see, because I know you didn't take the time to trace through everything that's going on the heap. Yeah, the list class is a linked list. Must have typed that before I said it. All right, so that's it. That's a linked list. This is everything I need to say about the structure of a linked list. So for each one of these data structures, the linked lists, trees, graphs, we're going to introduce the structure, and then we're going to talk about some algorithms that we can use to work with this structure. So the structure, not too much there. That's going to be the same with trees. The structure of a graph gets a little more complex, so we'll spend more time talking about that. But this is the structure. A linked list node that has a value and a next, which next is a reference to another node, then we're going to null terminate them. That's it. That's all I have to say about the structure of linked lists. So again, for interview questions, when we say, what's the structure of a linked list, there's not a whole lot you can say. Rattle off that stuff and you'll be good. And then the TA might ask you a follow-up question to make sure you didn't just memorize that line. But that's it. So what's really interesting is when we start talking about the algorithms. How are we going to work with this? How do we work with this list that's made up of separate nodes that have references to other nodes? So let's go through some algorithms and just talk about them. So, and let's just, we'll just do them rapid fire, and I'll show you a whole bunch of algorithms. Now I'm going to write these as recursive algorithms. One, so we get more practice with recursion. And two, because when we talk about trees, we almost have to use recursion. We could use loops when we work with trees, but my God, it's difficult. It is very tough to do, but it is possible. So I'm going to use recursion when we're talking about lists. So when we go into trees, it's not just coming out of nowhere like, oh, recursion. I haven't seen that in weeks. Plus, I think recursion is neat, so it's fun to use. I don't know who agrees with me on that one, but I'm going to use it anyway. I'm going to say that anyway. So with size, our base case is if next is null, then we know we're looking at the last element of a list. The size of that list is going to be 1. If next is not null, I'm going to compute the size of next. And this is in the linked list node class. This is a method of the linked list node. I'm going to compute the size of next, so that's the size of the rest of the list, excluding the element that I'm looking at right now, and plus 1. So if I have the size, if I say, hey, next element, what's the size of you, the list starting with you, and it reports back like, oh, 17. Well, if I refer to a node, which if that were the first node of the list, it's size 17, and I refer to that element, then the list that I refer to must be size 18. I'm going to return that to whoever asked. If the thing that asked was a linked list node that refers to me, they're going to say, well, I must be of size 19. They're going to keep returning until the head of the list, and it's going to return the full size of the list. Oh yeah, the train analogy. I should add that to lecture. Except the trains aren't all over in memory, is the only thing. It's like there's an activity we could do where I give you all, I've seen this before, I always wanted to do it, but I don't know if we can pull it off in a lecture hall, where I give you each an envelope, and the envelope has a value and the next envelope that should be read. And we say, who has the envelope that says you're the first one, and you shout out, and then somebody else is like, I have this value, and then we put together the linked list. It's fun, it helps you understand, but I don't know, in a lecture hall like this, it'd be tough. Maybe someday. So toString is very similar to compute size. It's very similar to compute size in that if next is null, we're just going to return the value .toString. So we wanted to take all the values and return them as a string. I'm going to say a comma-separated string here, just to choose a format. So if next is null, I have a list of one element, or I've reached the last element of the list that I'm converting to a string. So I'm going to take its value, convert it to a string with toString, and return that. Every object has a toString method. I'm going to take advantage of that fact and say, convert yourself to a string, and then I'll work with that string, just return it in this case. If it's not the last element of the list, I'm going to take the value at this node, convert it to a string, append a comma, and then call next.toString, which is the recursive call to this method. You know, so if you did this in a loop, it'd actually be pretty tricky to get the commas all organized. But with recursion, it's actually a trivial solution. No comma in the base case, commas in the recursive steps. Without that, you have to have a check like, is this the last element? If it's not the last element, don't add a comma. Or if it's the first element, don't prepend the comma if you're appending them that way. With recursion, it actually cleans up that question. Just add a comma only in the recursive step. if we have time at the end, we'll do the debugging demo, but I'll skip that at least for now so we can get through these slides, because I took so much time at the beginning. But I do recommend, even if I don't get to it, I'll probably get to it at least Friday. I'll do debugging demos. But if I don't get to it, I do recommend running the debugger and seeing how all this looks in memory. I'll at least get to it Friday. Friday's dedicated. The Friday of each week during LO3 is dedicated to examples, so I'll have plenty of time to run the debugger on Friday. So let's access the location of an element at a particular index. Index has to be in quotes because we now know that there's no such thing as an index in a linked list, but we can pretend there is and say, give me the value at what would be this index if you were an array. But index doesn't make sense if we don't have random access, if we don't have an array like that. So this is the apply method, or if you just use parentheses on a list, either way you've been doing it, this is effectively what's going to be happening in that. So apply of I, give me the value at index I of a linked list node. And we're going to return the entire node at that location. We're not just going to get the value of it. So if I is 0, just return this node. Else, call apply once, and then navigate I minus 1 more times. Make the recursive call for I minus 1 more times. So if we're saying apply of 4, we're effectively calling next 4 times. So if I is 0, we're calling apply 0 more times and just returning. But if I is not 0, we're going to call apply once, we're going to call next once, use up one of those, and then say you still have to call next I minus 1 times. And this is where we get that inefficiency, that O of n. Calling apply, accessing a value of a list like this, very, very slow, because we have to hop all over memory. We have to grab next, get that reference, go to that spot in RAM, or in the heap, call apply on it, which is going to go to the next one, which is going to go to the next one. We're hopping all over memory. We have no other choice. It's not like an array where we just do a little bit of math and go right to the element we're concerned with. Here we have to jump all over memory by calling next, dot next, dot next, dot next. We're hopping all around. It's slow. We have to go somewhere else in memory, read the next reference, go there, read the next reference, go there. Very, very slow. O of n runtime. Adding an element. To add an element, it's actually pretty easy with a list, at least with a mutable list like we have here. With Scala's immutable list, this is a little different. We'll talk about that on Wednesday. But adding an element, say we want to add an element with the value 2 right in between 3 and 1. To do that, we're going to create our new node and place it right after the node containing 3. By creating a new node, updating 3's next, which was referring to this node, have it now referred to the new node, and the new node's next is going to refer to the old next of the value that we're adding. So we're going to do this from the node before the location where we want to add the node. Create the node, refer to that node, and then the old next is the next of the new node. So we're going to slap that node in there and then update the references to be able to have that as part of our list, just by updating the next references of a few nodes. In the code, it looks like this. We're going to create inside the element before the location where we want to add. We're going to update its next to a new node with the element we want to add with a next of the old next of this node that we're adding it from. If we want to delete an element, we need a reference, similar to adding, we need a reference to the node before the node we want to delete. And this one's even simpler. We're going to update this next to be this node's next. So we're just going to update next to be that next node in the list. And the node that we're deleting still exists. It's still sitting there in memory, but we just bypassed it. We just went around it. So now that this list is no longer referred to by any node, or this node isn't referred to by any node in the list, it's effectively not part of the list anymore, and it's a prime candidate for garbage collection as long as nothing else refers to it. This is going to be cleaned up and destroyed by garbage collection. In the code, even simpler, this.next equals this.next.next. Make sure you don't call that on the last element of your list or things break. You'll get a null pointer exception. When next is null on toString? toString has a null check though. Would accessing an element in an array be any faster than a list? It's finding the element to access is what takes so long with the list. With a list, you have to keep calling, you have to keep accessing .next, 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 .next. With an array, you can access the element directly. This is assuming that you know the position in the data structure of the value you want to look at. So if you need the 100th element in an array, you go to index 99, you can jump right there and access that memory directly. With a list, you got to call .next. You got to go .next, .next, .next 99 times, which is going to be 99 operations, so we have linear runtime, instead of a multiplication, an addition, and we're reading the value already. No matter what it is, that was O of 1. It was a constant number of operations, no matter what n is, no matter what index we're reaching. So if you know the index, array is much faster to look up the value at that index. All right, finding a particular value. We have some value in the list. We want to find it based on equality, based on the equals method. If we want to find an element in a linked list, we have two base cases. If the element at this node is the value we're looking for, return this node. And we want to return the whole node. And whoever we're returning this to, they can call .value to get the value. But in this case, they already know what the value is. They're probably interested in the node itself or just the fact that it was found. So return it. If this.next is null, so the value isn't the one we're looking at, and we're looking at the last element of the list, we didn't find it. To signify that, we're going to return null. And if the caller sees a return value of null, that's our way of saying, hey, your value's not in this list. I don't know, try something else. Else, we're going to call find on next, on the next node. We're just going to pass the buck down to the next node of the list and say, hey, you look for this. And if that node can't find it, it'll go to the next one. You look for this. If we get all the way to the end of the list and nobody found the value, no node is referring to a value that matches that, we're going to get null, no return. Just as an example, here's a recursive version of it. We could do the same, or iterative version of this method. We could do everything iteratively for linked lists. But again, once we get to trees, we really have to embrace recursion. But this is what it would look like. We'll initialize our node to the head of the list. We're going to keep calling .next to update the node. For each node, check if that is the right value. And we're going to use this ugly return value in the middle of our code. If we get to the end of this list without ever returning, we're going to return null. Or we can use it recursively. I would argue the recursion is easier to read, but I know that's debatable. Especially if you're not used to recursion, that might be harder to read. For each, I have a function. I want to call it on every value in this linked list. We're going to call the function on the value for this node. Again, all these methods are inside the linked list node class. So this node's value. And then if there's another element, if this isn't the last element of the last node of the list, call for each on next. Make the recursive call. That'll go all the way down the list until it reaches null, calling that function on every single element. And the last one, we can squeeze this in. Oh, it's 240 already. So remember map, where we give it a function and return a new list with all the same elements, but with that function applied. We want to do that same thing. We're going to call the function on the value, get the new value. If this is the last node of the list, return a new node with the new value and next of null. If it's not the last one, return a new node with the new value, and next is the recursive call of map on the next value. And if we want to change the type, we're going to take another type parameter, have a function that converts the type, and then change all the types to type B, if that is something you want to do. All right, 2:40, so let's get out of here. Have a great day, everyone, and I'll see you Wednesday.